Yeah, welcome everyone. We're here for the Pangeo workshop with Tom Augspurger, Anderson Banihirwe, and Paige Martin. And I'm excited to hear about geospatial data. If you want to take it from there.
All right. Yeah, thank you so much. Thanks everyone for being here. Welcome to the Pangeo session at the Dask Summit. We're very excited to have 6 wonderful speakers. And we have quite a diverse range of topics that they'll be talking about. Some more science workflows, some on the technical aspects, and we'll also be hearing about teaching Dask. We will have 6 speakers for about 15 minutes, and then the last 30 minutes of the session will be a panel and Q&A time. So you can ask questions at that time. So without further ado, we will jump right in. So the first speaker will be Chelle Gentemann. Her talk is called Sea Dask Swim, Ocean Temperatures from Space. And if you would like to start sharing your screen, that would be great. Chelle is a senior scientist at Farallon Institute based in California. She has a physical oceanography background and has successfully championed many efforts in open science within the earth and climate sciences. And she's an expert in remote sensing for oceanography, which is what she'll be talking about today. So Chelle, take it away.
Great, can you hear me and see my screen?
Yes, we can.
Perfect. I chatted out a link. If you would like to run this code yourself, you can click on the top link and then sort of navigate through like I provided instructions so you can run the code yourself. And there's 2 files in that folder, one of which has all of the code run, and the other is where we're running the code. And I've already pre-run it just so we can take a look at it. So Dask is really useful for dealing with big satellite data sets. Satellite data sets are large. They tend to be really hard to move into memory unless they're a really low resolution average data set. And especially a lot of the science that we do now, we're moving towards higher resolution, both in time and space. And when we move towards those bigger data sets from the more recent satellite instruments, we start to very, very rapidly run into RAM issues. And opening even a single day of data becomes prohibitively difficult. It's slow, it's time consuming, and that's why doing sort of out of memory operations and using Dask and chunking becomes really important. So what I'm going to show you here is a tutorial that goes through 3 different types of sea surface temperature or SST data sets. And they're all on AWS. They're in the Open Data program, which is really great because you don't have to pay for egress. And these data sets are in NetCDF, they're in HDF5, and they're in XAR, but they're all fairly straightforward to read, with XAR being, of course, the easiest because it's cloud optimized. But these are really big data sets that you can analyze on the cloud without downloading the data. And so here we're going to first look at how to find an AWS public data set, and this tutorial includes sort of how to find things and navigate around the open data program. Because when you get to a web page like this, it tells you about the data set, but all I really want to, I want to know how to open it up. I want to know how to read it into and look and start exploring the data. And to me, this ARN address wasn't exactly clear how to get from that address to the data. And so that's part of what this tutorial demonstrates. So MER SST. MER is one of the data sets that's really, I think, xarray and Dask, it really highlights how useful they are. These data sets are global daily sea surface temperatures since 2002. So we have almost 20 years of daily global data sets at 1 kilometer resolution. It's about 3 terabytes of data, 3 to 4 terabytes of data. And it's all stored in the AWS Open Data Program on an S3 bucket. So if you run this cell, it's just importing some of the libraries that you're going to need. And then we use the file location, we use fsspec to map it. And then it's just one line. In one line, which is just xr.openzar, you give it your mapped key and it opens the data set so that you can start exploring it. If you look at this, and this is one thing I like, so when you type DSST, it then displays the data set. And you can see this is a really large data set. This is the entire data set opens up in a few seconds. This is a real success story right here. When we first created this data set, it took about 3 to 6 minutes, depending on the number of processors you had open. It took a long time to just access the metadata. And working with the Pangeo project, and Martin Durant and fsspec, we were able to improve fsspec so that it now opens in less than 3 seconds. And this is the way that open source software and communities are supposed to work together, right? So it's really nice to see that translation of like scientists finding difficulties and open source developers listening and being able to fix it really rapidly. The turnaround on this, I think, was just a couple months. And if you look at this data set, you can see that they're all in Dask arrays. Now these Dask arrays, it goes time, latitude, longitude. This particular MER has one big chunk in time, so it makes doing time series analysis really fast. If you want to do spatial analysis, there's a second version of MER available that's chunked more evenly in time and space. But these looking at the Dask array and looking at your chunk sizes is important when you start to do your analysis. You can, of course, explore your data sets and look at the metadata. You can also view them. So this is also really helpful. At least I find it really helpful when I start to use a data set for the first time to figure out, yeah, so I guess it's actually like 16 terabytes. Sorry, I thought it was smaller than that. And if we want to then go and read 10 years of data at one point, we can run this cell. And one of the powerful things about xarray is that you can ask it for what you want in language that you understand. So I can ask it for the time period that I want and a latitude and longitude rather than having to translate those into coordinate systems. And as a scientist, I really appreciate that because it makes my code really easy to understand and read and useful to others. And I can plot this. Now, this is, again, a huge data set, and I can plot this time series in 3 seconds, in part because of how we've chunked it, but mostly because it's in XAR. And these new cloud optimized formats have made accessing and exploring these data sets so incredibly fast. I can then go through, I can do a group by, I can do a climatology, calculate an anomaly, average that anomaly into monthly, and then plot both of those. Again, very, very quickly. And I find this code really easy to read. You're grouping it by time, day of year, you're taking the mean and time, and then I create the anomaly again using a group by, and then calculate it using resample to do a monthly average. And then I plot both of them below. I'm going to skip this next part, but it talks a little bit about how to understand the data a little bit better and go down to the geostationary data. So the geostationary data is from the GOES imagery satellite, and there's two GOES, there's an east, a west, and there's a Japanese satellite called Himawari. These data sets are all on AWS as part of the Open Dataset program, but they're in their native format of NetCDF. And what you have to do in order to read that data is read each one of those NetCDF files, and it can be quite slow. Now I've used a Dask delayed here, so I've used a decorator, and I've written a subroutine that goes through and uses OpenMF dataset to read in 1 day's worth of data. You could rewrite this subroutine to read just an hour, so a single file, and it would run faster. This is just sort of a generalized one to read a day. And it reads either east, west, or Himawari over Japan. Then we can go and we can actually use the Dask delayed, and it It's not actually doing anything yet. So this part runs really fast when I ask it to go get the data. And I'm looking at goes east here. So goes east looks over the Atlantic Ocean. And I'm doing a subset. Now here, because this is level 2 data, it's not mapped to a latitude and longitude. So these coordinates don't make a lot of sense yet. You would have to remap it into latitude and longitudes, which would be the next level up of satellite data if you wanted to ask for the data using latitude and longitude. I'm masking the data so that I only get cloud-free pixels, and then I'm making an image. And so this is just one time slice. This is hourly data. It's actually, there's the possibility of having more frequent than hourly data. But this is an hourly image, and you can see the Gulf Stream. So you can see the warm Gulf Stream coming up along off the coast. You can see some eddies. There's Cape Cod for reference. And this took 5 minutes to create a daily image, just to grab 1 hour. Now this is still fast because you don't have to download the data and image it, but it's slower than we'd like to be because of the data format. So I'm trying to explore how to speed that up, and we have some ideas, especially trying to get it into Pangeo and a xarray format. The Pangeo Forge is starting to work on that, I believe. And this is just if I took all of the ocean temperature data and created a mean for that day, then you have a really beautiful image. And then you start to be able to tell that, oh yes, this is the east coast of the United States, and here's the Gulf Stream beautifully as it goes off into the Atlantic Ocean. We have some Himawari data. So this is Japan, and we can do the Kuroshio current in the same way. And one of the things I've just started learning how to do is to visualize how Dask is looking at and how it's running that get geodata program to see what I can do to speed it up. And that visualize command can be useful to try and understand why your code is slower or faster. I haven't yet figured out how to fix it, but at least I can see it now. So it's a step forward. The next one is ERA5. And ERA5 is, again, one of these really huge data sets. And there's a subroutine in the code that reads all of the ERA5, again, using Dask delayed. And then you can open up ERA5. This data goes back, I'm just reading a couple years of data here, but this data goes back to 1979. And if you're willing to have a slower wall time, you can read all of that data right here. I think it takes about 5 or 6 minutes to read all of the data. And you can see this is hourly data, 25 kilometers, and your Dask chunk sizes. So this is actually chunked evenly in time and space, but it's still quite fast to just make a global image. And I think that this is one of the powerful things about, so now we've explored 3 different completely sea surface temperature data sets. We haven't downloaded any of them, but we're able to look at the metadata, we're able to visualize them, we're able to start trying to understand how we might use them together or with different data sets. And that's all through this lazy loading, because these data sets are way too large for me to open up and start playing around with on my laptop or my desktop computer. And being able to understand how it's chunked and sort of ignore that parallelization that happens when you just run these plot routines is really powerful as a scientist. And this is a time series. This is the last little bit. So this is a time series off of Taiwan, actually. And one thing that you can notice even from this short time series, the temperature has an annual cycle. And it's getting warmer and warmer and warmer. And this is where this area has been experiencing record warmth. And storms in this region have been tied to the California wildfires, actually. This is a few of those storms. Those hurricanes churn up the water and cause little decreases in the ocean temperature. And as those storms stir up the atmosphere as well, they set off a wave that goes all the way across and can cause extreme winds in California. So these warm temperatures in Taiwan are somehow linked to fires where I live. And that's it. So thank you.
Thank you so much, Chelle. That was really interesting to see kind of an example workflow. All right, next up I think we are just going to jump to the next speaker. And again, questions will be at the end during our panel and Q&A session. Julius Busecke is next. His talk will be called Dask and the Ocean Death Zones, Lessons from a Real-Life Earth Science Workflow with the Pangeo Stack. So Julius is a research scientist in the Climate Data Science Lab at Lamont Doherty Earth Observatory at Columbia University in New York. And he's passionate about a lot of things, including physical and biogeochemical oceanography, and has contributed to many Pangeo packages, including XGCM. And yeah, today he'll be giving us an example workflow. So take it away.
Can you hear me?
Yes. Yep.
Awesome. And you see as well.
Yep.
Yeah, first of all, let me thank you all for organizing this very interesting session. And what I'm going to try to do today is actually, I'm not going to show a single code cell. I'm just going to try to sort of give a brief overview of my of the project that I've worked on and sort of try to point out how sort of what a realistic workflow, what that actually involves and some of sort of the lessons I learned and pain points I experienced. All right. Okay, so the depth zones was a bit of a clickbait. Usually you call them oxygen minimum zones. And what this picture here shows is oxygen concentrations around the globe at 250-meter depth. And you can see that these red areas are sort of these areas of interest where you have very low oxygen concentration. In this case, for my study, we call everything that's lower than 80 micromole per kilogram an oxygen minimum zone. And furthermore, we're going to concentrate on the Pacific only since it's the largest of these oxygen minimum zones. So why do we actually care about oxygen minimum zones, you might ask? There's sort of two main reasons. One is they have an effect on larger ecosystems, since the area of the tropical Pacific is one of the most productive and lucrative fishing areas in the world. There's sort of an economic impact, but then you also have an impact on the larger scale Earth system, because basically within these very low oxygen concentration regions, that's sort of the area where greenhouse gases are actually released from the ocean. And so if you're increasing the volume of these areas, there's sort of a possibility that more greenhouse gases are released and sort of that loops into a positive feedback cycle. So it's important to know how they're going to evolve in the future. And actually, that's sort of the theme of this study that is submitted to AGU Advances, and you can check out the preprint link if you upload the presentation. I can also put that in a chat a little later. It turns out that sort of the part that is really important for figuring out whether oxygen minimum zones are going to expand is actually looking at the thermocline. That's sort of where you don't have a lot of historic oxygen minimum zones, but you can sort of see here, this is the prediction of 14, I believe, CMIP6 models that simulate oxygen output over the historical period and then sort of the most strongly forced future scenario. And you can see that within the thermocline, very coherently, all of these models actually predict an increase of volume. And that eventually dominates the expansion of the oxygen minimum zone throughout the whole domain. Just to give you a little bit of context, this little harmless looking plot took me months of my life, and in the end I had to, for this one, I had to crunch I think over 100 terabytes of data, and so obviously Dask was not only nice to have, but really sort of a must, because you can't load all of that into a single machine, even on most HPCs. In order to get sort of these new results that we're getting, previous studies were really sort of suggesting that that most of these models are not sure about their projections. They were basically going into different directions, some even showing a contraction of the oxygen minimum zone. The key to arrive at that conclusion was really to go from a view of depth coordinates, as you can see here in the upper picture, into density coordinates. So this is actually not showing oxygen, but ocean salinity. But for the sake of demonstration, you can sort of see that that blue pattern there is sort of a very low tongue of salinity, but it sort of moves along these white lines, which are lines of constant density. And this is sort of something that in oceanography is a very common thing. Usually properties or tracers are transported along lines of constant density. And so one of the ways to sort of to really clarify where oxygen minimum zones are expanding was actually this conversion from depth coordinates into density coordinates. And that actually is something that, that is pretty well solved. XGCM does a very good and efficient job of that. And that's sort of thanks to the integration with Dask, but also Number. The sort of coordinate transformation problem can really sort of be reduced to a one-dimensional transformation, because the ocean is just so much wider than it is deep. So it's very flat. So you can really assume that everything you have to do has to be done within sort of a one-dimensional profile, and then you can sort of efficiently vectorize that a lot around large arrays, and then you can sort of execute that with Dask on existing chunks. But so you might say, okay, so that's it. That's what you wanted to tell us. Obviously, that's not the case. The fact that this is now showing at the very bottom of it just implies that there's many more steps involved before I can actually run this very computationally extensive step. And sort of this is my sort of outline of my workflow. And I've tried to sort of split it up into some of the smaller parts. So the model output here was actually downloaded. This was not done in the cloud, but I'm going to talk about that a little later. But basically, sort of the model output was downloaded to a HPC system over at Princeton University. And then I set up a custom intake ESM catalog that basically enables you to easily load all of these many data sets into xarray data sets. And then sort of over time, sort of this project really motivated mainly my work on CMIP6 preprocessing, which is really sort of a preprocessing package that enables CMIP6 data to be truly analysis ready, because there's sort of issues you can see here that have to do with different namings and sort of different modeling centers or different output files not really adhering to very strict conventions. Then another really important step that is not a part of CMIP6 preprocessing, but I'm working on that, is sort of removing control run drift. So you basically have to, for each model data set, you have to find the corresponding pre-industrial control run without forcing, sort of calculate a linear trend over it and then subtract that from the data. And this has to be done at every grid point. So this is quite an intensive task that is sort of done in parallel. And then I'm just applying that correction within this workflow. And then for some of the models, at least at the beginning of this was basically I had to recalculate some of the grid metrics. It's not that big of a problem anymore. One other big thing is that, especially for biogeochemical variables, they're often given in a coarser grid in the CMIP output. So we had to, I basically opted to interpolate them back onto the native grid. This is done with XESMF and actually worked pretty well. I then basically was able to combine variables and sort of do other steps that basically relied on several variables. And that basically was removing the mixed layer and then calculate some additional variables like the potential density that we need to actually transform it into a density space and apparent oxygen utilization, etc. These are all more packages to sort of say this is sort of a fullish Pangeo stack that is used here. And so the amazing thing is this all pretty much worked with Dask. You could just lazily layer this on and actually do quality control within and actually look at some of the time slices, and it just worked. But then I wanted to basically compute the whole thing and save it out. And well, I think this is sort of a common situation. And when people like me, who I would say is sort of an xarray Dasker, try to actually save out the whole data set, you run into this problem that for not really apparent reason at the beginning, your data set will basically at the end, your workers will fill up the memory and will crash, and basically diagnosing that can be a whole hassle. In the end, I had to basically save small time slices in a for loop. That's obviously not, I'm not very proud of that, but it worked. So I guess then coming to the stuff I've learned, first of all, you all, and by that I mean like Dask developers and generally the Pangeo community is awesome. All of these packages to the most degree worked pretty flawlessly. I would have probably given up on this whole project if there wasn't such a support from the community and all of these great packages that already existed. So big thanks to everyone who's involved in any way in any of these packages. The second part that I think I underappreciated at the beginning was the sort of migration ability of Dask. I was able to prototype on my laptop, actually prototype some of it in the Pangeo cloud, but then eventually moved everything to an HPC system, and it all pretty much worked. So that's really great. Maybe some of the stuff that you should avoid. Don't combine any data sets if you don't have to. At the beginning, I tried to basically make from every model and all of the members and everything put into one giant data set because that seems just nice in terms of bookkeeping. But that led to a whole host of problems, some of which are solved, but others are generally, I think, that's sort of my advice within sort of CMIP6 pre-processing. Sort of you go through different stages based on your scientific questions. Sometimes you need several variables. If you don't need it, inject your heavy computation before that and then combine afterwards. That's sort of just a practical tip. Sort of these persistent pain points, I think it's important. It's like this problem might not be super embarrassingly parallel, but it should still work. All of these steps can be applied in a for loop. So there's nothing that really prevents this from working. It's just that I think it just gets too complex and it just requires a lot of temporary saves. And that's still something I'm working on. And it's usually, even if you take parts out, then it fails at a different step. It's sort of very hard to get a grasp on what is happening with Dask if it actually fails. And I think what Chelle was saying is sort of that also applies to me. I'm just now sort of getting into the habit of actually maybe digging a bit deeper. And I think this might apply to a lot of people who come from xarray. It really sort of, it's amazing that Dask just works under the hood, but it also presents sort of a problem when you then actually run into problems. And I think a whole bunch of this might just be sort of a translation, sort of getting into the documentation of Dask, which is truly amazing once you get into it, but often it's just a matter of understanding vocabulary. And maybe there's some way that sort of the xarray community can provide some more entry points to that documentation. I guess going forward with this project, just to wrap up, I really want to get more of these workflows truly in the cloud. This one has still been done on an HPC. I hope that maybe if the reviewers take a little bit, I'm able to sort of send in the final version with a fully reproducible notebook that runs in the cloud. But we'll see. Let's hope the review doesn't take that long. But I think it's really sort of providing these actual real world use cases is valuable for both Dask development and for open science. Because sometimes it's really just like the simple example that you're trying, sort of the minimal reproducible example just doesn't cut it. It works fine. And then you add all of these steps and as a user, at least, I then don't understand why things go wrong. So it might be nice to have these things in the cloud so that people who knew more about Dask can readily sort of dig into it. One of the things that I'm planning to do next is sort of, I talked about the detrending and sort of that's on my list to sort of have derived data sets in the cloud. So basically go from cloud data, cloud processing, and then produce another cloud data set like these control run transfers. If you want to know more about the science, I can post that link a little bit later. And generally, I think if you're interested in CMIP6 data, I would really appreciate it if you check out CMIP6 pre-processing, and if you find any problems, get involved or get in touch in any way, shape, or form. I really sort of want to make this the go-to package to make CMIP6 really analysis ready. Thank you.
Thanks, Julius. That was really great. And I think it would be great if you could add the links that you're mentioning to your paper, maybe to CMIP6 pre-processing. You could do it in the chat, or we also do have a Slack channel for this workshop. So that might be better for longevity. Well, when this chat goes away. Yeah, thanks. That was really, really great. Okay, we will move on to the next speaker, which is Rob Emanuele. And his talk will be using Stack to catalog spatiotemporal datasets. Rob is a geospatial architect working at Microsoft. And yeah, today he'll be talking about cataloging datasets using Stack, or the spatiotemporal asset catalog. Go for it, Rob.
Awesome, thanks a lot. Yeah, thanks. I am not a Earth data scientist. I like to build tools for you all to use. So today I'm not going to be showing any cool charts. We're going to be talking about metadata specs and how to actually use these specifications. So not maybe as exciting as the actual science, but important nonetheless. So I put in a motivation slide just to kind of like get a flavor of like, yeah, we're working with really big data. We can't load it all. I think Chelle's presentation did a really good job of that, kind of saying, opening up even some of these large like netcdf files is difficult. So how do we start to like optimize that? We need to actually provide the metadata necessary that allows for this type of lazy loading. Nobody's has an HPC system that can open up all of Sentinel-2, although if we used all the cloud, we probably could. So that's where spatiotemporal asset catalogs comes in. It's working towards enabling online search and discovery of geospatial assets. And for those of you not familiar with Stack, really what it defines a set of JSON schemas for encoding metadata about spatiotemporal data. It actually comes from historically like Earth observation community, sort of like remote sensing satellite imagery type folk that were sort of inventing their own sort of metadata standards as they built out sort of cataloging systems, and all got together and said, hey, how would we like start to be consistent about this and on GitHub and in a community-driven way. So there's a set of core definition. So yes, it's kind of based in Earth observation, but it's meant to capture all spatiotemporal data, or at least like be able to represent any spatiotemporal data. If it's in space and time, Stack should be able to represent it. There's a set of core definitions that are necessarily like pretty abstract with core and community extensions. So the value of Stack is really like the extensions that add schemas to specify data types for specific data formats or domains. And yeah, we're really close to a 1.0 release. We're in release candidate 4. So if you have any final comments on Stack, get them in before we before we go ahead and release. Along with the metadata definitions, right? There's the concept of a Stack API, because just recording the metadata is enough. We need the ability to index it and then expose it on the web. So this actually is a separate spec that defines open API schemas for searching and discovering Stack metadata. It aligns with the OGC API features, right? This is a sort of different approach to specification creation. It's kind of implementation driven. We really value seeing implementations of something that works, and then slowly that makes it into a spec. But we play nicely with other standards bodies like the OGC, really try to align and extend some of the really core specifications there, including OGC API features. It includes a search endpoint for spatiotemporal and attribute queries within and across collections, and I'll talk about what collections are in a second. The Stack API specification is a little bit behind the core Stack, but everything's sort of moving to 1.0 hopefully in this year. So the core of Stack is these sort of 3 types, pretty general, easy to get confused, but there's these catalogs, collections, and items. Catalogs are really just any sort of grouping of the other types of things. Collection is much like a catalog, but it also provides additional metadata and usually is grouped by a specific like sensor, like you'd have a Landsat collection or Sentinel collection or GOES collection. And then items are really the GeoJSON feature that represents a discrete set of data assets. So, if I have my cloud optimized geotiffs that all represent bands of a single satellite image capture, those would be assets within an item. So made a couple diagrams to try to make this a little more visual. So catalog has basically like dead simple ID, title, description, also some other attributes. A collection, again, it's just like a catalog, except it has sort of the license that you can define as this openly licensed data, et cetera. The extent, both the spatial extent and the temporal extent, as well as the people who provided the data and summaries of the items that it contains. And then an item, again, is a GeoJSON feature that contains a geometry and also properties that can contain an arbitrary amount of data and can use extensions to sort of specify what the data contains in a machine readable way. So this is really generic. It kind of creates a graph of connected elements of metadata. So you can lay it out in whatever way you want, right? There's these links that link the catalogs to other catalogs or collections, links items, and again, as I mentioned, items have assets, which are the actual like data file assets. They also can contain links to, for instance, like browser pages or visualizations or other types of other items, even if they were derived from, if you want to track provenance or different versions of the items. The Stack API really lays out a stack catalog in, a stack catalog in a specific way. There's a landing page, which is a actual catalog. It itself contains collections, and each collection contains items. And then, so the main use for the API is that you're not actually browsing through these things like a file browser. You're performing searches based on time and space and attributes against the collections or across collections. And then I mentioned extensions. Those really are the sort of core value of Stack, because it allows different domains, different data formats to all place their own type of standardized metadata into these, and lay it over this structure. So for instance, in here, we see in line 5, there's a set of Stack extensions. The EO is for Earth observation, SAT is for satellite, view is for like these view angles, right? And they're all defining properties that are actually have values over here. And then you can also notice Aster, which is the collection this item is a part of, has its own sort of extension. You're not restricted to having a specific extension. You can kind of just do that colon prefix, and maybe at some point there'd be a JSON schema that would define a true extension, but also you can have arbitrary metadata contained in these items. So just to make this a little more concrete, I'm going to actually switch over to a browser and go to this Planetary Computer page. I'll look at the documentation. So Planetary Computer is a number of components, but one of the things that we host is a Stack API that's publicly accessible. You can hit it. And you can see, like, not a lot of surface area here. We can query for collections, the items of the collections, and also perform these searches. If I actually go to the API, we can start to look at this, these JSON items. This is the landing page, which again is just a catalog, right? And it has a number of links. If I go ahead and go to the Sentinel-2 L2A, the level 2 data that we host, you can see that there is, it looks like a catalog, but actually there's a bunch of information, like the extent of the basically the globe, because it's a global data set, the providers that provided the data, also summaries for various properties of the items that are contained. So it's really rich metadata that's sort of machine readable and standardized, so that you can sort of know where to look for all of this data in these JSON elements. And then if I go ahead and look at the items here, we can see that we get a GeoJSON feature collection back, where each feature is an item. And again, we have sort of the SAT and the EO and the proj, the projection extensions that specify information about the item generally. And then we have our assets, like say like the second band. I forget what the second band is, but if I look at the EO bands here, I can see that band 2 is the common name is blue, so that's the blue band, right? I also have projection information, which allows me all of the information to actually understand how to load up parts of these cloud optimized geotiffs. So I actually don't even have to read the entire file with the information that I have contained in this metadata. I can read windows of tiles, and that's like really important for this type of lazy loading applications that we saw earlier. Great, so moving kind of quickly, I just want to point out a couple projects that are kind of core to the Python ecosystem that I think would be useful for folks to know. PyStack is an implementation of these core types in a Pythonic interface, including many of the common extensions that you would want to write with. It also performs JSON schema validation. So if you're using, if you want to like explore Stack, PyStack is a great window into that. And also PyStack client uses PyStack under the covers with requests to go ahead and hit the APIs. I'll just mention that there's a GitHub organization called Stack Utils that both of those projects are under. Go ahead and explore that whole organization because there's a lot of awesome tooling to work with Stack in a number of different languages, including with things like xarray and Dask. And then 2 open questions I just want to leave with. I guess I'm doing okay on time. There's a question about representing XAR and things like MetsVF in Stack. There is a data cube extension that defines dimensional properties for things like XAR datasets. And so this is sort of a work in progress. And I think there's a lot of work, on the intake Stack side, and there's a number of projects trying to figure out like how do we represent the types of data that the Pangeo ecosystem typically has been working with, like climate data, like more XAR data sets in Stack, and what is the relationship between those two approaches? Because it's sort of another open question here is like, when is it more appropriate to represent a data set as XAR, which gives you that JSON metadata that allows for that lazy loading, and when can a Stack API with cloud optimized geotiffs as items suffice? For instance, Chelle had mentioned GOES data, and we're actually in the process of determining how Microsoft AI for Earth will be hosting GOES data. And there's a question of like, is there a chunking strategy for XAR that would be more optimal for the type of analytics that people want to do? Or would we be able to just take each of those HDF files, export them as cloud optimized geotiffs, enable that same sort of cloud optimized format, and then enable search using a Stack API to load things into Dask, into xarrays. And I think we're kind of leaning towards the cloud optimized geotiff side. So would be curious if anybody had any thoughts on that. But yeah, this is a lot of general information about Stack and how we're how Stack is encoding standardized geospatial metadata. But I just want to mention that Stack and Dask is awesome. I don't have a lot of experience with Dask. I come from I was a core developer on GeoTrellis and in the Apache Spark ecosystem. So some of those single worker failure problems kind of ring true from my years my work years back. But I work with Tom, and he's been showing me a lot of like what Dask can do and the Pangeo ecosystem can do, and it's really awesome to see, even with just XAR providing enough data metadata to do lazy loading of these large distributed data sets is awesome. And I think Stack is going to provide a lot of the same capabilities with things like cloud optimized geotiffs. So I invite you to see Tom's talk tomorrow, where he'll dive into the projects like StackBRT and Stack that and Intake Stack that like help users take Stack APIs, take Stack metadata, and turn it into xarrays that can be worked with in a distributed manner on Dask. So yeah. And then if you'd like to learn more and collaborate, stackspec.org is sort of the portal. Also, we use Gitter. There's some links here. I'll tweet out my slide deck. But yeah, thanks for inviting me, and great to hear the other presentations. Great talking to you.
Thanks so much, Rob. That was really interesting, really nice to hear about kind of the inner workings of Stack, which is very important to the Pangeo community. Great. And we will move on to the next speaker, which will be Deepak Cherian, who will talk about distributed group by with Dask arrays. Deepak is a project scientist and physical oceanographer at the National Center for Atmospheric Research, or NCAR, based in Colorado, and is a core developer of X-ray and XGCM. And we'll be talking today about a specific aspect of Dask, namely the group by function. So yeah, Deepak, it's all yours.
Thank you, Paige, and thank you to the organizers for inviting me. My name is Deepak Cherian. I'm one of many xarray maintainers, and as Paige said, I also spend a lot of time doing oceanography, but today I'm going to talk about a little side project I've been working on for the last 2 months, where I've been thinking about group by operations for Dask arrays. And I basically dived into how Dask data frame does it, and then dived into how Dask array implements a lot of things, and then I survived. So this is my story of things I learned. There's code and a package associated with this doc. So the repo is up here. So you should all go try it out. And so, as a high level motivation, let's think about this data set. It's output from a climate model, the GFDL CM 2.6, and it's ocean output. This is available on the Pangeo cloud. So that was great. It was very easy to log in and just try things. So here's a wrapper for the temperature field. So this is ocean temperature. So it's got 4 dimensions. Time, S in this case is a vertical dimension. There's a Y and then an X. It's about half a terabyte. So it's pretty big, but it's chunked really nicely. So about 200 MB chunks. But the chunk size, the chunks shape is kind of important here. So this is monthly mean data. And the chunks are, so you have 1 chunk in time, 5 in depth, and then all of X and Y is in 1 chunk. So, it's these really big. Your chunk just really small in time, and each chunk is a monthly mean, and there's about 240 time steps here. And so there's one data set, and I'm going to try 2 different group by operations. The first one is what climate scientists would call a climatology. So in this case, we do a monthly climatology. The way you would do that with xarray is to say ds.temp.group by time.month.mean. So if you don't know xarray, the syntax comes straight from pandas. If you know pandas, it should look familiar. The idea here is you take all the Januaries and you average them together, all the Februaries, average them together, and so on and so forth. And so, here's what the output looks like. You see there are 12 months. So you basically have an average January, an average February, and so on. And you preserve all the other 3 dimensions. This ends up being pretty good, actually. So you end up with 8,000 tasks. The output chunks are decent size. Everything's great. And you should be able to get this to work. Here's a second group by problem. And this I'm calling it a regional mean. You may want to do this, let's say, when you have a variable called regions that divides up the globe into, say, the Pacific Ocean, the Atlantic Ocean, the Arctic, the Southern Ocean, etc. In this case, just for demonstration purposes, I chose longitudinal bins, and there are about 9 of them. And so I did .group by regions.mean, and the whole thing explodes, right? So suddenly I have 100,000 tasks. The ending chunk sizes are really small, 54 kilobytes. You end up with crazy amounts of tasks, crazy chunks. Doesn't look so good. And if you try to compute this, So at a high level concept, on the left-hand side, where you do the monthly climatology, because you're chunked as 1 block contains 1 month, you basically have 1 group per block. And on the right-hand side, because these are longitudinal bins or in X, you have many groups per block. So this is the kind of conceptual division here. And if you try to compute that regional mean on the Pangeo cloud, you end up in this kind of like very familiar death spiral where you try it. In the beginning, it goes well. And then your dashboard starts to look like this. And then you're like, maybe this will finish. And then not really, it just grinds to a halt. And then you're like, should I rechunk? Should I throw more workers? This should be somewhat familiar to many people on this call, I imagine. So it doesn't really work, this whole regional mean business. And so let's think about why that doesn't work. And so here's a little schematic. On the left is a kind of visualization of my array. And in this case, again, each color here represents a different group. And so this is one array with 4 blocks, so 1, 2, 3, and 4. And in each of them, I have some kind of random distribution of groups. And so here's what xarray does, is it knows where all these groups are. So it goes through, sticks this array in a little centrifuge, and then pulls out 4 different arrays. So there are 4 groups in total. It makes 4 new Dask arrays. And it does that with this like crazy massive arrows, which is trying to illustrate all the communication that happens when you stitch up these 4 new arrays. And then on each array, it's going to call .mean, basically. And so you take all those values and you end up with one output value. And then you stitch them together to get your final output. So at a high level, I think of this as a kind of communicate. So in the beginning, you just take all of this data and send it everywhere, and then you reduce it. And for this case, where you have many groups per block, what happens is you take each block and you kind of like shred it up. And so I suspect that this is where the whole algorithm kind of starts to fall apart. And so you end up with this situation that is kind of described in this slightly modified quote from Silicon Valley, which is the code is not really optimal for what we're trying to do, for the computation that we're trying to do. So let's see what we can do if the Dask worker was not going to apologize for the code base. So here's the same array. Again, there are 4 blocks, and we're thinking about many groups per block. And what we're going to do first is do a reduction. So step 1 is to do a group by on each block. So this is kind of like a blockwise call or a map blocks. People may have heard this term. And I'm interested in the mean. What I'm going to do is instead blockwise compute the sum and the count, so the number of observations in each group. And this is what Dask calls internally a chunk step. And so you go from one block that's kind of big to a very small block, right? So this is for each group that you will have 2 values, a sum and a count. The next step is to take the adjacent blocks and kind of combine them together. So you kind of stitch them together to form a new array. And at this point, you kind of have to do some, so here, for example, this block only had 2 groups, the next block had 4. So when you stitch them together, you gotta have some fill values and stuff. So they're details, but that's what you do. And then we reduce this again. Again, you do a group by reduce, so you get down to 1. At that point, you're doing, let's sum the sums and you sum the counts, because that makes sense. And this is what Dask calls a combined step. And you just keep going. So it just depends on how many input blocks you have. Over here, I had 4. So at this point, you bring these 2 together, keep going, and you end up with, at the end, with 1 block that has all the sums and all the counts. You can divide those 2 and you get the mean. So this graph, as you can see, looks in this very schematic form, looks very clean. It's what Dask calls a tree reduce. And it's how Dask actually implements a lot of the core reductions like sum and mean, etc. So this is where I dove into Dask array and really started to appreciate how things work at a deeper level. So when we do this, this algorithm is kind of implemented in this repo. I changed the API like yesterday, so it's very work in progress, but you can do things. So here's me trying to do that regional mean. The output kind of looks pretty decent, 9,000 tasks, very awesome. The chunks are still small, but that's because it's just a big reduction. And then when you try to compute it, it looks amazing. The task stream is great. There are no white gaps. The cluster does really well. The memory usage is really low. At this snapshot, it was 13 gigabytes. It actually completed in 10 minutes with 12 workers on the Pangeo cloud. And used a maximum of 18 gigabytes of memory. So if I had this data set on an external hard disk, I could do this on my laptop. It's totally doable. And so it works really well for this regional mean case that totally fails with the current xarray implementation. And so here's again my 1 data set and 2 group bys. Again, on the left is the monthly mean. On the right is the regional mean. So here's it now with this new package. It works really well for the regional mean case, as I showed you. The monthly mean, it actually doesn't work so well. You end up with these giant chunks. So the reason is because, again, conceptually, remember, on the right-hand side, you have many groups per block. So the initial reduction, when you do the mean on each block, you end up using up a lot of your data really early on. On the left-hand side, when you have the Januaries, and you combine nearby blocks, you don't actually reduce because it's a January and then a February. So all you end up doing is reading data and concatenating for a while before you can actually reduce, right? You have to go like 13 blocks over to find in the next January that will then get reduced. If that was a little confusing, basically what happens is you get a giant memory spike in the beginning and the cluster just gives up, right? So you end up getting this is what your Dask scheduler is going to do to you. And so at a high level, for this case, where there are many groups per block, that's when the initial blockwise reduction is really effective at using up your data quickly. And then it works really well. The left-hand side, where you have like few groups per block, I think the current xarray strategy is actually pretty optimal and it should work. So that's kind of at a high level. Kind of on the API side, these are basically the 3 main entry points. There's one which is just group by reduce. So you take a Dask array, and you group by another Dask array, and you say, give me the mean. There's a really convenient one, which is an xarray group by reduce, where you can just give it an existing xarray group by object and say, hey, give me the mean. So that's just for convenience. You can like plug it in your code today and like not change anything. And then the last one is this native xarray interface that eventually I'm hoping we should allow some opt-in through xarray itself, where you give it an xarray object, data set, data array. Both I think will work. And you can group by a data array, call the mean, and in theory, you should do all this. A complication is because you're doing this, this whole like tree reduction thing. If you want to apply a custom function that is not implemented already, you need to think in these steps. So there's an API here that I, again, directly copied from Dask data frame, which was pretty great. So, here's the name of an aggregation. This is how I define the mean. The first step is chunk, which says, hey, on a blockwise thing, you compute the sum and you compute the counts. When you combine your intermediate results, you want to sum the sums and then sum the counts. And then at the end, you give this custom function, a little lambda here where you do sum divided by count, and you get the final one. And then, as I mentioned, there's a little reindexing step. So you kind of want to stick a fill value in there that kind of makes sense. But it's doable. You just have to think in this kind of stepwise manner. Some features, like I said, I learned a lot while I was doing it. So the implementation is a little low level and complicated. But because of that, it has some cool features, which is that it supports argmin and argmax, which is a fun problem to think of and to learn from in Dask array. You can also do max, min, variance, standard deviation, all the standard things. It tries to minimize tasks because usually I find that Pangeo workloads tend to have this issue. So a lot of stuff computation is just stuffed in a task. So the sum and the count is calculated in the same task itself. So that's why you get those really low task counts. And one really cool feature is you don't actually have to know what the group labels are, not necessarily anyway. And so you can actually discover the groups at compute time, which is kind of cool. The core group by operations come from this package called NumPy groupies. And that has actually an optional opt-in to number aggregation, which hasn't been enabled yet, but in principle, we can do this. So finally, this is my final slide. So basically, there are two ways to do group by today. One is the current xarray approach. The other is this new approach that I've been experimenting with. There are various trade-offs. The current xarray one really only works if you group by a NumPy array because it needs to know where the groups are to do it. This one, you can do Dask or NumPy. On the left, it works really well when there are few to one group per block, I think. This approach of initial reduction works really well when you have many groups. And then there's some, on the left, you have one output chunk per group. On the right, you get all the groups in one output chunk. Dask data frame does something really clever so you can opt out of this basically. And I've implemented a very simple version. So this is in theory fixable. So it's maybe not really a trade-off. And arbitrary functions are really easy to apply today with the xarray code. It's a little more complicated. You have to think in this stepwise manner, but it's totally doable. So I'm going to stop there. Thank you for listening. And there's this little repo here, which is not very imaginatively named, Dask group by. You can try it and open issues and help me clean up the code. Thank you.
Thanks, Deepak. That was a great talk. I'll echo some of what has been said in the chat, that your diagrams were really great and really helpful for illustrating the problem that you were discussing. Since we have like 1 minute, I'll ask, someone wanted to know what software you used to make those.
It was I used a matplotlib really. I just drew squares and then copied it over to Google Slides.
Nice. All right. Yeah, cool. Thank you. That was very interesting. All right, moving on to the next speaker, which is Haiying Xu. And she'll be talking about Pangeo benchmarking analysis, object storage versus POSIX file system. Haiying is a software engineer, also at the National Center for Atmospheric Research, or NCAR. And she'll be telling us today about benchmarking, or assessing the differences in performance and scalability between object and file storage systems when carrying out computations with the Pangeo software stack. And I think Tom has the pre-recorded video ready to go.
Hi, welcome to Pangeo workshop. I'm Haiying Xu. Today, I'm going to talk about Pangeo benchmarking analysis on object storage versus POSIX file system. Before I start my talk, I'd like to ask you a question. Who knows ZAR file? Is ZAR file only useful on object storage system? I will present my finding and questions based on our project Pangeo benchmarking analysis. This work was collaborated by Haiying, Kevin Powell, and Anderson Banihirwe at the National Center for Atmospheric Research. Both of them helped me a lot on the project. Today, I will be covering 6 key points. First, I will reiterate our motivation to the work. Then the next thing I will share with you the varied testing condition for the benchmark and how to set up benchmark. Afterwards, I will show you the benchmark performance results and our discussion about the results. At the end, I will discuss our future work. First, I definitely want to answer the question that I just asked at the beginning to the scientist. Secondly, we want to make this become a standard tool to benchmark Pangeo stack. We will encourage users to use it and share their results at our cloud storage space, and our tool will publish the plots online automatically. In this way, we can see how performance changes among different HPC and cloud platforms, and also along different versions of Pangeo stack. Third, we want to compare read-write throughput of ZAR data format versus netcdf data format. If you don't know ZAR or netcdf, I will talk about those in the next few slides. Lastly, we want to show the performance and the scalability of object storage versus POSIX file system. Which one has advantages over the other? Now let's talk about varied testing conditions. We used the 5 testing conditions. First one is the storage system, which is object storage versus POSIX file system. We used the active scale object storage that is purchased by Inca from Quantum Inc. The active object storage has a transfer rate over multiple streams at almost 8 GB per second. It is using real-time system management console, CLI, and RESTful API for management interfaces. It is also using RESTful S3 for connectivity protocols. S3 object storage is essentially a key value storage system. The keys are unique strings and values are bytes of data. Data is read and written using HTTP calls. The POSIX file system we used are data director network storage at Xiangyan, which has 200 gigabytes per second transfer rate. It is POSIX compliant. Next, we have I/O format is a testing condition, which is netcdf versus ZAR. netcdf is both a data format and I/O library for self-describing array-like data. It is commonly used by geoscientists to read, write, and share scientific data. It is widely used in climatology, meteorology, oceanography, and GIS application for weather forecasting and climate change research. ZAR is a data format and a Python I/O library too. It is for chunked, compressed, multi-dimensional array. ZAR can be saved as a key value store on object storage and has as a hierarchical directory store on POSIX file system. The third condition is the read or write. However, the netcdf API with the Dask does not allow direct write to object storage yet. So in this study, we skipped the netcdf S3 write testing. The fourth is the cluster size. We use computer node count to change the cluster size. The last one is the chunk size. Because Dask and ZAR are all using chunking scheme, by varying the chunk size, we can find out which in-memory chunk size provides best read and write throughput performance. Now we want to talk about how to set up benchmarking. First, using xarray data array, create a 3-dimensional variable which has time, longitude, and latitude. Then we randomly generate data itself. We use the Dask cluster to distributedly read and write this array to netcdf or ZAR file. Thus, we create a Dask cluster using a PBS job scheduler by specifying number of nodes, number of workers, and memory usage at a Xiangyan supercomputer at NCAR. This is how we set up hardware for the benchmarking. For software testing, we have two different settings. One is the weak scaling analysis. This one measures read and write throughput for fixed dataset size per processor as the node count varies. This analysis similarizes CESM simulation from node resolution with a few nodes to high resolution with many nodes. CESM, which is the Earth system model that simulates past, present, and future climate. So for the second analysis, we use strong scaling analysis. It measures read and write throughput for fixed total dataset size. Here we used 460 gigabyte as the node count varies. It is similar as the scaling CESM simulation with a fixed resolution from a low number of nodes to high number of nodes. Now let me present the performance results. First, we talk about the weak scaling read. Let me remind you what is weak scaling. Weak scaling is defined as how the runtime varies with the number of processors for a fixed file size per processor. The read study shows that NetDF on POSIX roughly 20% faster than ZAR on POSIX file system, and both are 10 times faster than ZAR on S3 read, which is almost certainly caused by the S3 store having a maximum 8 gigabytes per second aggregate stream. The best reading scaling for ZAR on POSIX was found using 768 megabyte chunk size, which is in red line. This line shows roughly linear scaling with the number of nodes, which is as we expected. Also, the larger chunk size reduced the total number of chunks, leading to less communication overhead, but the larger memory usage. Next, we talk about weak scaling write performance results. ZAR on POSIX is 10 times faster than NetDF on POSIX with one node, and 9 times faster on 12 node. ZAR on S3 is 50% slower on one node than NetDF, but is 45% faster on 12 nodes than NetDF. Please note here, on this write plot, NetDF on POSIX and ZAR on S3 have same y-axis. ZAR on POSIX write has much larger y-axis value. This makes ZAR look like an appealing option for actual CESM model output, and not simply just data analysis. In the following, I will show you the strong scaling results. Strong scaling is defined as how the runtime varies with the number of processors for fixed total file size. First, we talk about the POSIX file system. Read of NetDF data from POSIX file system are 0 to 45% faster than reads of ZAR on POSIX system. The comparison between the two at a chunk size of 64 megabytes on one node gives us a 45% difference and 0% difference on 12 nodes. And the average is 30% faster on 6 nodes than ZAR on POSIX file system and 50% faster on 12 nodes for any other chunk size. This indicates NetDF has better performance on POSIX, but from the plot we can see ZAR scales better. ZAR tests have larger errors as well. Next, we talk about the read of NetDF data from S3. NetDF read on S3 are 3% slower to 30% faster, 13% faster than read ZAR on S3 with one node, and roughly 6% faster on 6 nodes and 8% faster on 12 nodes. Overall, there is no significant difference between these two data formats. This could be due to S3 have 8 gigabytes per second aggregate transfer rate. If we could run this benchmark on clouds and read-write locally to a S3 storage, we may get better read-write throughput. Dask parallelism scales well with both data formats until using 6 nodes, starting to saturate when using 12 nodes. And NetDF appears saturated sooner. Also, chunk size 192 is the optimal chunk size on ZAR S3 read. We also performed one single strong scaling test on random read access between NetDF versus ZAR. Comparing to the continuous read in the same condition, we got that ZAR on POSIX is better on random read than NetStF on POSIX. This is because it takes less time on seeking when randomly access ZAR format. You can see ZAR random access is 69% faster than NetStF, even though ZAR continuous access is 13% slower than NetStF. We review all the performance results. The conclusions are on object storage, ZAR read throughput is almost the same as NetStF. There's no significant difference. On POSIX file system, NetStF format read a little faster. It's around 20 to 45% faster. However, ZAR scales better, and the ZAR random access throughput is better too. ZAR format is definitely beneficial to geoscience community since it has a lossy compression with a fast write throughput and also always has a very flexible storage API. It can write to different cloud platforms, the database and the POSIX file system with one abstract API easily. If we want to optimize ZAR, we can set a skip instant cache as false. Then this can enable cache on read and write ZAR. Also, we can set use listing cache as true. This will enable direct listing caching and reduce the time to spend on find the files. At the end, I want to talk about the future work. First, we want to containerize the benchmarking with Docker for cloud and the Singularity for HPC. That will make users easily to perform the benchmark. Secondly, we want to compare write performance against pNetStF. pNetStF is a high-performance parallel I/O library to access NetStF file. It enabled a synchronous I/O mode already and used in current CESM simulation I/O output. Finally, we want to benchmark on high throughput scalable object storage such as AWS, Google Cloud, or Microsoft Azure. That will be more interesting. Also, we definitely want to benchmark with cost in mind. That's my talk. Hope you enjoy it. Thank you.
All right. Thanks, Haiying. Thanks, Tom, for playing that for us. I believe that, oh, yep, Haiying is here. So she will be here for the panel and Q&A session that is coming up after the next talk. All right, moving on to the next speaker. Next is Damien Irving. And the title of his talk is What and How Should We Be Teaching Atmosphere and Ocean Scientists About Dask? Yep, great, sharing the screen. So Damien is the Pangeo systems developer at CSIRO's Climate Science Center, based out of Tasmania. So it's quite early in the morning. Thanks for joining us at this time. He has extensive experience teaching with software carpentry and will be giving us some tips now on teaching Dask to climate scientists. Go for it.
Thanks, Paige. It's early in the morning for you too.
It is.
Yeah, so I wanted to talk a bit today about kind of round out the session by talking about what we should be teaching atmosphere and ocean scientists about Dask. I guess a bit of an interesting side note, I recently finished up 5 years of postdoc life and took a job, kind of a data science software development role at CSIRO, and my job title is Pangeo systems developer. So it's kind of cool and crazy to see Pangeo popping up in actual job titles, which is kind of interesting. But I guess the reason I'm interested in talking about how we teach Dask to people is that for a number of years now, I've been involved with a non-profit organization called the Carpentries that some of you might have heard of, that teach coding and data science skills to researchers around the world. And you might have come across one of the kind of programs, one or more of the programs under the Carpentries banner, either data carpentry, library carpentry, or software carpentry. This slide's a couple of years old now, but it kind of gets across the main point that here's a map of all the 2-day software carpentry workshops that have been run since 2012. So it's it's become something of a phenomenon. It's really grown pretty rapidly over the years, and now there are hundreds of carpentry workshops happening all around the world every year, which is really cool. And there's some stats just from I think it was our 2019 annual report. So yeah, it's become a really big and kind of exciting project to be a part of. And so for those who haven't been to a carpentry's workshop before, basically there's a big focus on programming best practices. So you'll analyze some data and do something useful, create a plot and things like that. But the focus is very much on, how to write modular, reusable, testable code, kind of best practices, more so than learning the nitty gritty details of any particular library. And it's kind of hope that once you've got the kind of, the best practices and you've got a mental framework to hang new information off when you come across it, then hopefully you'll be able to teach yourself the details of any particular library that you need to use for your analysis going forward. And the instructors at our workshops are trained. So there's an instructor training course where you learn some basic kind of educational pedagogy principles, things like that. At the workshops, if you've ever been to one, there's a lot of live coding. So no slides or anything, a lot of live coding, people seeing you do things and stuff up things live, and a really high helper to learner ratio when we break out into exercises and things, so you can have a lot of good discussions with people and help them understand. And so I started running generic software carpentry workshops on the day before the National Conference of the Australian Meteorological and Oceanographic Society back in 2013, and kept doing that every year. And they were kind of really, really well received. A lot of people wanted to do them. They were usually oversubscribed. And so I bit the bullet in 2018, and instead of using the generic software carpentry materials, wrote a discipline-specific set of lessons for data carpentry. The data carpentry program is all about data-specific or discipline-specific lesson materials. So I did that for PyAOS, Python for Atmosphere and Ocean Science. And so every year since then at the AMOS conference, we've been running this data carpentry PyAOS workshop. And then with the help of other, qualified carpentry instructors around the globe who work in kind of atmosphere and ocean science, we've run a number of workshops at Woods Hole Oceanographic Institute, at the Australian Bureau of Meteorology. NOAA's been using the lesson materials in some workshops they've done recently. We use them at the AMS Python short course this year. So really kind of growing the global community of people around these lessons and getting them out there. And so I guess relevant to the Dask session today is, by popular demand, about a year ago, maybe 2 years ago, we added a large data lesson onto the end of the kind of workshop syllabus, if you like. And so basically what happens is, up until that point in the workshop, we've just been working with a very small data set that people can easily download onto their laptops. So it's like 5 years of monthly rainfall data from a relatively low resolution CMIP6 model. And then so we kind of posed the question in this final large data lesson is, well, what if we're not working with this tiny little data set, but we're working with a much bigger one? So in this case, we use 150 years of daily maximum rainfall data from one of the really high resolution CMIP6 models. It's about 45 gig of data, this data set. And so basically, in terms of how we deliver this lesson, the instructor downloads this 45 gig data set onto their laptop before the workshop, because everyone's basically working on their laptop. Tends to be the safest way to run these workshops if you're relying on internet connections and 30 people in a room all logging onto Binder Hub or something at the same time. You can often have problems, so we tend to be laptop based. And then the instructor in this lesson kind of gives a 10 or 15 minute demo where they work through the process of analyzing this 45 gig data set to plot the daily maximum precipitation across the globe. And then it's not optimal, but the situation, what we're doing at the moment is the learners then work on some exercises after this demo that don't actually require them to download and process the data. So they think about alternatives to Dask for dealing with big data. Like maybe they could have looped through each individual file one at a time and process them instead, process subregions or something in some kind of a loop, and then talk about pros and cons of, you know, why you might want to use Dask versus that kind of approach and vice versa. We get them to set up a Dask client so they can at least see how much RAM they have on their computer and kind of what they're working with. And we get them to think about projects they're working on and how Dask might help with that. But I guess that's a bit of a limitation at the moment in that they don't get their hands dirty in the workshop. In terms of I guess, what we teach, so while the instructor's going through this process of plotting the daily rainfall, maximum daily rainfall, there's a number of, I guess, core concepts we want to hit and best practices we want to hit as we go through. So obviously one of the first things we talk about is lazy loading, which is obviously very important. We're dealing with large data sets. Then we talk a little bit about chunking. We talk a bit about the optimal size for chunks because that's a question people often have. But beyond talking about the fact that on the Dask website, you know, it says the optimal somewhere between, I think, 10 megabytes and a gig. That's about as deep as we go. We talk about the importance of which axis of the data you chunk along. So in this case, the data on disk in the netcdf files is a series of files chunked by time. And so making sure we're chunking by time when we're doing that in xarray as well. Then what we do during the lesson is that we first process the data, do this daily maximum precipitation calculation just on one core. So we basically just demonstrate the fact that, hey, isn't this cool? This data set's too big for our computer, and yet Dask xarray processes it chunk by chunk instead of all at once. And we've been able to do this calculation even though the data's too big for our laptop. That's cool. And I think that we time the process, takes about, well, on my laptop, when I'm teaching, that takes about 3.5 minutes. Then we set up a Dask client and coordinate the thing over the 4 cores on your laptop. And then on mine, at least, that takes about 2.5 minutes. And so then we can kind of talk about the fact that, well, in this case, that was good. Doing things in parallel made it faster, but it wasn't, you know, a quarter of the time that it took to do it on a single core. And then we can talk about the fact, you know, that there's a time cost associated with, you know, coordinating all the tasks and things like that. And so you don't always have a situation where parallel is best, if you like. Sometimes the cost of setting up all these tasks is actually greater than the time savings from running things in parallel. Then we touch on, well, what do I do if I'm not using, say, the max function that's already Dask aware and already built into xarray, if I'm using some random function out of the SciPy library or something like that, how do I make that Dask aware so I can leverage Dask? And so we point people towards apply ufunc and map blocks, but we don't actually do it. And I think what I need to do is actually write in a little example into the lessons of actually doing it and making a non-Dask aware function Dask aware. Because I mean, there are some nice notes online about how to do that and things, but I still think if you're relatively new to it, having a very simple example would be helpful. And then obviously, as I mentioned before in the exercises, the learners think a bit about other alternatives to dealing with big data and why Dask might be better and in which situations it might not be. So yeah, that's kind of where we're at the moment. So we've got this 10 or 15 minute demo in the lessons, and these are, I guess, the core concepts we're trying to get across to people. And I guess my motivation for presenting today was to really kind of ask the question of this community and of, you know, have I missed any core concepts? Are there things that people really need to know when they start using Dask that we're not covering and we need to? Is there a better way to teach this stuff? Are we being silly worrying about connection issues to Binder Hub, or is there a good way to kind of let people get their hands dirty with big data when you've got, you know, a workshop environment, when you've got 30 people in the same room connecting to the same Wi-Fi connection, and things like that. And then I'm also kind of interested in, you know, what would you add if you didn't have just 15 minutes, but you had an hour or two to talk about the things you need to know about Dask? What would you add in that context? And if it's really compelling, I'd definitely be open to making this lesson longer in the data carpentry stuff. yeah, that's all I've got for now, and I'll just put the GitHub link up there. I'm very happy always for people to put issues on the GitHub repo for the lessons, and love having discussions with people about potential extra lessons to add in there. So really invite people to check out that page. But otherwise, thanks for listening.
Thanks, Damien. That was really interesting. I think a great way to round out the talks in this session. I already see that someone has responded to your questions in the chat, so you might want to check that out. And of course, we can continue that conversation now as we start the panel and Q&A. So I will hand it off to Anderson.
Thank you, Paige. All right. So yeah, we have a couple questions from the audience, and then some other general discussion topics. So let's see, we have 30 minutes. So we'll try to get a few questions from the audience, and then if we have more time, then we'll actually address some of the more general discussion topics. So let's see. I guess we should probably start with, there was a question for Julius, and the question was actually about, how did you coordinate your workflow with so many data processing steps? Did you produce any intermediate files? Did you use any workflow manager, such as Makefile, SnakeMake, or was it all in one notebook?
Not one notebook, but I think it's pretty much 3 notebooks. And over the course of the project, the amount of temporary data, actually I got to go back to Princeton. I'm definitely like busting the file system there, but has changed quite a lot. At some point I was so frustrated, I literally between every step, I saved things out. That was obviously a bit too much, but then I sort of pruned things away and found out that really sort of you can layer almost all of it into the graph and then really save up small time steps. The one thing that I pre-saved, and I think that's just necessary, is the detrending step. For that one, I actually use rechunker and basically convert everything into time chunks. I think that's just like something that's impossible to get into one consistent Dask graph. But yeah, I'd also still a work in progress. I think that I'm already learning so much that I really want to try to go back, or do I?
Right, thanks. Let's see. So our next question is for Rob. Are there any advantages of COG over XAR that you're learning towards for the geostationary operational environment satellite data? I think there was an answer in the chat, but it might be worth discussing in general.
Yeah, yes. So one of the things that I am learning and kind of considering is, what is the metadata that can be loaded sort of statically, and what metadata should be queryable. So with a Stack API, you have the ability to like perform a query for a specific set of data sets, and then you're never holding on to sort of the detailed metadata that Stack provides for more items than you really want to load. Whereas I believe with XAR, there's this sort of header file type thing that has the coordinates and a lot of the different types of metadata that you actually load up as a single read. Correct me if I'm wrong. So if you did have like really dense data sets, that sort of header information might get really big, and more dynamic sort of like top level metadata query would be good. Also, yeah, I think that for regular gridded array data, XAR makes a lot of sense. But for things like satellite imagery where it's not pixel aligned, there's just sort of arbitrary footprints, and each footprint has its own sort of grid of the Earth, and there's they share a projection system, but it's not as nicely chunkable. That's where sort of like cloud optimized geotiffs representing that single time point and of that area is I think maybe a better choice.
Actually, this is a follow-up question from me. So could you use the groups in XAR to save that kind of data sets that don't align properly? Like still have the same single XAR store, but then in different groups, the same concept that you'd find in HDF and CDF. Do you think that would work? Or
As I do when these types of questions come up, I'm going to defer to Tom for an answer for that.
Yeah, I'm not sure. I think you probably could, but it doesn't feel quite natural because I feel like the groups of a data set should be fixed. And if you have like new data coming in off the sensor and you're like adding new groups as it comes in, that feels a bit weird, but I could be misunderstanding.
I mean, XAR groups are basically just directories of different files, and we don't really have any tools that can leverage those groups. So it's not clear to me what you gain by putting them all in one group versus just having many data sets.
good.
I do love that. Like the question is why not use XAR? Why use Cog instead of XAR? At least like the one community where that would be like the default choice.
All right. So let's see. Our next question is for Deepak. Can xarrays group by use the Dask group by approach automatically based on some simple heuristics? For instance, number of groups versus number of chunks.
Yeah, I've been thinking about that. So you basically have to know how the groups are distributed in the box, right? So that means, if you're grouping by a NumPy array, I think you could figure that out and then come up with a decent heuristic. But if you're grouping by a Dask array, then yeah, you just need extra information to provide to the problem to do it well. And anecdotally, I know Dask data frame has trouble with group bys too. It's for this reason. It really just depends on how the groups are distributed.
You do a group by and then in the string, time dot month or whatever. In that case, that's like the NumPy array, right? Since you're grouping by a coordinate.
Yes.
Is that most commonly like the most common grouping, or do people group by variables a lot too?
That's extremely common. So
cool.
Yeah.
All right. So there's one question from Alex. Has anyone used the rechunker library, and what is the experience like? So we have Ryan, but if someone else want to answer that, please unmute yourself and.
Yes, I have. And I think by far was one of the most satisfying experiences because it literally just worked. There's not a single instance when, except when I dialed up the memory too far. But rechunker was really that one point where you're just I didn't have that anxiety that things would just crash at the end after I've used it a couple of times. So thank you, everyone.
Good. All right. So our next question is from Stefan. So Stefan is curious, in general terms, when does Dask work well for big data workflows? When does it not work? Anyone? Chelle or anyone who's working with big data?
I think this is a question that we're all asking because I feel like Julius said the same thing I said, which is I have all these things I want to do and I'm just becoming a really, really expert kernel killer. And it's very frustrating because sometimes things just seem to work like magic, and other times my kernel just dies and I don't know why. And I really, and like Julius does, and Ray Bell suggested this as well, then I resort to doing loops, and I don't actually understand why that works, and not I don't have a lot of insight into how to troubleshoot these problems. And my default is to start creating loops or subsets of doing the data and getting it to work. But it's really frustrating, and it's hard to communicate that knowledge to other people who I have a feeling that there's probably this big community of people who are just like me, where we don't know much and we're just trying to break things on accident.
We've all been there.
I'm going to jump in and say, I think at least with this group, one issue is that xarray is too good at abstracting things. It's really easy to just call group by. and then it fails just because it's not appropriate for the problem. Resample is a common case where that happens. The resampling algorithm is absolutely not optimal. Sometimes it's better to just use coarsen, and it would work beautifully well. So I think that's one of the problems, really, is that xarray is abstracted so much that it's hard for people to get expertise in what it's doing under the hood and what you should be doing.
Yeah, actually, oh, go ahead, Matt.
You go ahead.
I was actually going to ask a follow-up question, but if you actually want to.
Okay, so I'll answer. So I talked to, I mean, if I were to aggregate, I'm gonna give a technical answer. So if I were to aggregate the problems that I hear from this group, they fall into two categories. One, like I ran out of memory, like I started seeing all these red and orange bars on my dashboards, and like things get bad, things grind down. But really, like this workflow should be something that Dask should be able to figure out. Like there should be a path through this workflow in a low memory way. Why isn't that running well? And a lot of that ends up with Dask sort of not having a good sense for the memory that your task will produce or not produce. And that's like a focus of active work right now. So there's a guy right now, Crusader Key, people may know him. He's also an xarray maintainer. He's working full-time on active memory management. This is like a multi-month effort, but like hopefully in 3 to 6 months, like those problems will be lessened. The second thing I often hear is like graphs take a long time. Like if I'm operating on 50 gigabytes, totally fine. 50 terabytes, things kind of grind down a little bit. That may or not be the case for some folks, depending on your scale. But that's also an active area of effort. There is a workshop, I think on Friday or in 2 days, about a group across company group working on that. That's again, maybe like a 3 to 6 months out solution. But I think what's good news is that these problems are really common, both from this group and from other groups. And so like they're actually like, of the two major sort of open source efforts that like people around me are working on, like those are the two efforts. They're also hard. I was really excited to see Deepak's talk today, which like gets around it just by making smarter graphs. And that's also an option, I think, for this community to think about.
I think one challenge that I've had and I've seen users have is that the normal tools that we would show in a Dask demo, like visualizing the task graph, when you're in a territory, when you're about to kill your workers, that's usually a task graph that you can't look at. Like the first worker you'll kill is the one you try to visualize the task graph on. Usually like the node that you've generated the bomb that you're about to send to the cluster. So something that could represent the task graphs at maybe a higher order level and say like this thing has a nasty signature, and if you send that out, you're in trouble.
Yeah, so there's also a lot of work on task groups right now inside the scheduler, which are these like groupings of individual tasks. And so that like helps solve a scalability problem with the kind of stuff you're talking about. That's also an effort that I'm actually really interested at Coiled, because we want to capture that information, like the right level of information. It'd also be nice to have that kind of data be stored somewhere else, so it's not on you to capture it, but it just like is being captured real time by some external process. And that's, I guess I'm like, all of your problems will be magically fixed in 3 to 6 months, maybe is what I'm saying. And I'm lying about at least 2 of them because that doesn't happen. But
I just wanted to jump in for a second, and I linked to the upstream issue Matt was referencing about visualizing task groups. And also I wanted to quickly plug the first category of problems that Matt was talking about that Guido's working on. He's actually giving a talk tomorrow if folks are interested and can attend that. So just giving a quick plug for that.
Ryan, want to say something?
Just a really quick comment based on having done this for a long time. You know, an intermediate strategy that tends to work to solve some class of problems is to just write your functions at a little bit lower level. So in xarray, we like to write a bunch of xarray code, you know, xarray, sell this, and xarray, you know, add this array to that array. And if you can just reduce what you want to do to a single function that you can send through sort of map blocks or apply ufunc, it often works a lot better. You know, we in the long term, we can hope that Dask will optimize things in certain ways. In the short term, that's a strategy that you can adopt today to make certain workflows work better. Right at lower level.
Hey, Simon. Yeah, go ahead.
Hi, thanks. Sorry, can you hear me
Yes.
reasonably well?
Yeah.
Okay, yeah, so I think I'm very interested in all this too, because I think in radio astronomy, we've got, well, we're running into this, similar problems. But I think what our perception is that there's a intersection between array broadcasting and the Dask ordering that tends to introduce like a breadth first search element into how tasks are scheduled. So intuitively, when one is expecting fairly independent parallel streams, what you're actually getting is this wavefront. Sorry, this is the most intuitive way I can explain it. And I just want to pitch a talk in our session because I don't think it's advertised very well, but one of our members will be sort of trying to drill into sort of technical explanations for this and like in a deep down graph sense, and like seeing what you can do with graph manipulation. But this might be very similar to what Crusader Key might be doing too. So I just wanted to mention that.
Thanks for that. So actually, I wanted to go back to what Ryan mentioned about coming up with simple examples or simple code snippets that allows you to do the debugging. And one of the things that I've heard from people is that most of the examples you find from the documentations are too trivial to actually use, at least for people actually to learn how to either diagnose some of these issues. And I wonder if actually people have some ideas on how at least we could do better on that front, because I feel like there's a lack of course, domain-specific examples, and the ones that are usually provided through documentation are too trivial and not realistic, to the point that I think for new users, it can be a bit confusing to figure out how to either isolate these issues or figure out actually exactly what's going on. So I wonder if people have ideas on that. Anyone can
I think in that sense, like Dask is actually succeeding too much for its own good, because it's provided these fantastic collections and what I would say are NumPy semantics on top of a distributed processing system. So it just affords people the ability to, create these parallel distributed programs, but it also hides that from them. And I think it gets to the point where people just don't know what's going on under the hood. So it's kind of a victim of its own success, in my opinion. And distributed programming is hard.
Yeah, I guess I have a follow-up question on that, but I'm curious how much that is like. Are there examples where this has been solved well, and maybe what can we learn from that? Like, I don't know if there are some, like maybe there are some of these examples like these more mature data frame abstractions, or these sort of like distributed SQL type things. Like, I guess I'm curious, like do these other, is this like how unique are the challenges that are being faced in sort of the Pangeo community versus the more general large scale data analysis? I don't know if anyone has any thoughts on that.
Wants to go first?
I think it'd be helpful for Julius and I and others to just document and share where we run into these issues and how we've solved them. And it may not be, it's going to be clunky, but it shows a path forward.
Yeah, maybe let me also add, I think that sort of what Ryan is suggesting is probably sort of a way forward, but it's at least to me, maybe I have to just sort of give up that sentiment that will always work. I think the advantage of this sort of xarray abstracted way of doing things is that you can really sort of, this is sort of how I go from an explorational analysis to something that eventually runs. That's sort of the ultimate dream, right? Like the suggestion here is that you can sort of do the exploration, but then you kind of have to recode everything and put it in a map blocks call. And it's probably sort of the right way to go forward. But like if Dask could actually do that efficiently, this sort of from my first idea and just coding up 3 lines to a finished product, I mean, that would be just so amazing. And I'm kind of still not willing to give up on that. But then again, I also don't understand enough to make that judgment call. And I think maybe just like sort of on the uniqueness, I don't think it's just unique in geosciences, but I think that is very prevalent, these sort of very custom solutions, like coming up with like, it's not just analyzing a data frame and then sort of counting or something. Like it's very much sort of several layers of these very custom operations that then basically cause trouble along the line. And that's sort of, I think, very typical in geoscience, but maybe not exclusively there.
So if I can jump in briefly, like with some context here, like this is a wonderful problem that we have, right? Like we're saying, oh, I can only analyze 50 gigabytes of data, or I can only analyze things on 100 worker cluster, right? Whereas 3 years ago, like we were really excited about working on a laptop out of core memory, right? And a year from now, like we're going to add another order of magnitude onto our capabilities, right? But we're still going to be in that situation where we're like, man, but I really want to hit that petabyte scale, and I have to pull out all of these tricks. Like we're always going to be able to get to a bigger scale by pulling out tricks. But my hope is that, like, if folks wait around for a while, like Dask will catch up to where you are today. Unfortunately, by that time, you will have moved on and you will have deeper needs, and will always be chasing what people want to do. But just, I mean, again, just like looking backwards a little bit, like it's fantastic what the distance that we've come in this short time. But we're always going to feel that pain as well. Like there's a pessimistic and an optimistic approach that we can always have, and we're always going to be in that tension.
Unless someone.
Well, just one other comment. I mean, thanks, Matt, for that context. I totally agree. And I mean, we've come a long way since our first little X-ray task demos. Yeah, I guess one thing I wonder about is to what extent maybe maybe we need to start thinking about like sort of breaking this Dask array was kind of like a really great way to sort of build xarray, for example, on top of Dask really easily. But maybe there's a need for, like, I guess this is coming up with things like group by operations, for example. Maybe there's a need to start building more sort of specialized types of operations that sort of understand the nature of the computation more. I guess this is happening already. You're talking about at a lower level, but maybe also even for things like like an xarray group by, for example, might be something that needs to be sort of handled at a higher level of abstraction.
Yeah, that'd be great. I mean, this is the Deepak approach.
Good.
Yeah, I have one suggestion. Sorry, just that since this block chunk based, is that possible? We can for that map block function, we can have some kind of different function underneath it, so we can implement a different operation on different chunks. Is that possible?
Not directly through map blocks, since it takes a function, but if you do use the lower level like Dask graph approach, end of the day, a Dask graph is like functions called on chunks of data. So you can build up a custom Dask graph that does your own function on the right block, or you can use something like Dask delayed to do a similar thing.
Okay, yeah, because I thought, I'm not sure if other scientists, because I need maybe apply different compressor on each block. If I can find a way to just using one function to call different compressor, then I can do different things on each block. I'm not sure if anybody else has this kind of needs, but I think this is going to be solve a lot of problems as well.
Thank you, Haiying. I guess, so I have one more, we have a few minutes. I have one more question, and this one is geared towards actually education. And it's a comment or a question from Damien, which is there actually a better way to teach this stuff? Like basically, how do we make it easier for new users to learn about Dask and xarray without getting them to shoot themselves in the foot? Yeah, so people have some ideas or thoughts on that? Or Deepak, do you want to say something, or was that from the previous discussion?
Yeah, that was from the previous discussion, sorry.
Okay. One thing I always wonder about is when to basically introduce like the concept of chunks, because you can get like pretty far with just the magic of xarray. You don't even have to explicitly say it. You can just read an xarray data set that happens to be chunked and not know that you're using Dask at all, and stuff will happen in parallel or distributed if you happen to have a client set up. And that like is cool, but you can fall pretty hard on your face once the chunking structure is not appropriate for your problem. So it's like an interesting tension there between when to introduce this very, very complicated concept of chunking and how it interacts with your computation. So yeah, not a solution at all, but another question.
I think also covering the Dask graph and just kind of common pitfalls with that, and also tying into what you were saying, Tom, just kind of discussing like ideal chunk size, as well as like how to chunk your data based on the computations and sort of some best practices for that. So yeah.
There was a great tutorial earlier today by James and Julia it was designed to be like your second tutorial on Dask, which assumed you had taken a Dask tutorial, and then went into like customization options and like interesting debugging and how to play around with stuff. I wonder if maybe there's like room for an xarray tutorial that is in a similar nature, not the 101 course, but the 102 course.
Yeah, I think that like at least my experience has been that you need that chunks probably maybe need to be in that, even like the 15-minute overview type thing, because otherwise you're guaranteed things. Things may go wrong even if you have the right chunks, but if you have the wrong chunks, they're guaranteed to break. And you kind of need to understand a little bit about how you're parallelizing, like you do sort of need a mental model of how your work is parallelized in order to sort of effectively use most of these tools still today.
I wonder if this would be good. Like these all sound like great ideas. Who's going to do these ideas? I wonder if some of the institutions that are out there, maybe like NCAR or like the Met Office historically, that sometimes have some extra bandwidth. Like this might be an interesting opportunity to have a lot of impact. I think those groups understand the community really well and understand the technical problem well enough. And they're the kind of people who I think if they produced, a short course or something like that, would be maybe both in scope and impactful. Try to get someone else to do the work.
Yeah, I know that there's also plans to incorporate at least some of this teaching within the Project Pythia, which is focused on developing curriculum related to this. So that's cooperation or project that's NCAR, University at Albany, and a couple other groups too.
That sounds really promising.
Yeah, Pangeo 2.0, I guess. Let's see. So we have 6 minutes. Let's see if there's one more question, and then let's see. So this is probably the last question. Is the Pangeo community leveraging all aspects of Dask, or are there features of Dask that could benefit the community that are currently underutilized? Any takers?
I might actually jump in and hope Matt or someone else, or maybe in Simon might say something. I've chatted with Simon, and it sounds like he and his group are using annotations very successfully, which is a very new feature. So I'd be curious to hear what he has to say about it.
Go, Simon, go.
Yeah, so I think we're still experimenting with that, and I think there's a tension there because we can get good. Well, first, what we found was that we could get good scheduling by annotating absolutely every array in the application, which was quite intrusive. And so now we're trying to do like a hybrid approach where we annotate basically our root nodes and then try and spread the annotations out through the rest of the graph. So that's also why I didn't really submit a talk, because I don't think we've come up with a killer workflow yet, as it were, but I think we're close. Yeah.
Maybe just
I think like there might be more information in our in the radio astronomy session on Thursday.
I'll maybe try to give like not something you can really use today, but a teaser of what's happening now. So usually when you construct an X-ray computation on your Python process, there's a high level graph that's telling Dask what's going to happen. Dask then crunches that down into lots of little tasks that are kind of opaque, and it sends those off to the scheduler, which then schedules them however it can. But the scheduler has lost all of the higher level information that was really present in the code that you wrote. And what's happening now with Dask is that we're actually starting to send that more high level information up to the scheduler. So that'll decrease a lot of pain with large graphs. It will also provide a lot of opportunities for Dask to think at a higher level and make some smarter decisions. Annotations is one example of that. Annotations are able to sort of go along that pipeline. But there's other things that will come about as a result of that. And that's, I think, going to be a good opportunity to solve many of the problems we've talked about here, but also maybe come up with some new thoughts, right? We can start thinking about, annotation is a good example. Like, this part of my computation is special in some way. It should run on GPUs, or this part of the computation, needs to run on single core workers because the functions are really big for some reason, or something like that. And so there's a bit more of an opening that's happening over the next few months.
Thank you, Matt. And with that, I guess we're coming to the end. So I just wanted to take time to thank our speakers and my co-organizers, Paige and Tom, and the audience as well for the good questions and the discussion. And I also wanted to take time to plug. So on Friday, there's an xarray user workshop. So if you're interested in xarray, and to actually learn more about the internals of xarray and things like that, I highly recommend attending that workshop on Friday. And with that, I'll basically let you go to the next sessions, or go do whatever is on your calendar. For those, it's bedtime, and I guess good night. And then for those of us who are still here, then probably see you around. With that, should probably just close this one out. Thank you, everyone.
Thanks, Anderson. Thanks, everyone.